as a consultant for a large company was a little interesting. They were mostly structural and civil engineers, so I'll talk to you a little bit about bridges, for example, and buildings. But I was also getting work because of my me working with Tom Eager. I was getting all sorts of work as well. So I was kind of the go-to guy for mechanics and materials out there, out of 300, 400 people. So I ended up becoming more and more diversified as time was going on. Professor Eager asked me to, if I wanted to prepare this relatively general talk, because today we'll talk about safety factor as it applies to different industries. And there is a handout if you came after the others. The idea here is not to be, super specific. There are a few ideas that I want to carry out to you, one of which is we don't really design structures stronger than they need to be. So when we say we have a safety factor of 3, that's based on a nominal analysis. It doesn't take into account all the worst case scenarios that we know of or we don't know of. So when you take everything into account, it's more from experience that we know if we build it twice as strong, we should be able to go through a 50 or 100-year life with a probability of failure of the order of 10 minus 6 or something like that. So that's a little bit how we're going to go today in saying the safety factor of 2 is not for somebody to use. I say I have a safety factor of 2. Well, I'm going to put only half the boats. I don't really need the others. That's not how it works. It's in reality, you only have a margin of, say, 20% of something of that order. And it's just for whatever mistakes along the way or improper use and any condition that was not considered in the overall analysis of the original design and normal statistics. So that's a little bit what we're going to go through. There'll be quite a few examples, and I'll talk a little bit. I know Professor Eager talked to you guys a little bit about welds and weld inspection. So we're going to go back a little bit to welds and bolts today. And we'll tie back into how different people do design in different industries at the very end. Just to bring in that highlight, I think you guys' work is relatively diversified. So I think it's good to realize if it's an FAA type analysis, then sure, it's got its own set of requirements. If it's not, if it's a secondary structure or if it's a research type structure, then you have to come up with your own ways of doing the design. A lot of times, if you design and you make a sophisticated analysis, you think that you know better what the capacity is and what the strength is, but there are still these factors that you don't expect and that may happen that will influence. That's why you still need a margin. Even if you calculate the worst case scenario that you think could happen, there may be something else that you didn't think of that would also happen, and that's why we have safety factors. The definition, we have 2 of them. One is the failure load versus the allowable load. I think it's a little bit more used. The second one about the yield stress and the working stress is more for pressure vessels. And you already see when we're moving forward that pressure vessels have a higher safety factor, but it relates to how it's calculated. If you're doing a working stress, you're already saying, I'm not taking into account water hammers, for example. So you know that you're actually going to have higher stresses than what you're designing for. It's just because you don't really know them, then the analysis is scaled back into something that's simpler. If you want to do a more sophisticated analysis, you'll say, well, I know my pressure is going to be twice as high because of transient situations. And my best way to deal with that is essentially I double the stress level here at the bottom, and then I can reduce my safety factor by a factor of 2. It turns out to be the same. It depends on how detailed you're going to be. And what it also means is you have to be really clear, and that's why it's based on experience, on what you mean by that safety factor. Is it divided by the allowable load or the working stress, for example? If you don't know that, you'll have a problem defining what your safety factor should be for a given structure. When somebody that's been working, say, in automotive, say they use a safety factor of 3, but they have a very particular way of calculating what the capacity is, the failure load, and what is an allowable load for that structure based on wheel data. They put sensor on the wheels and they go through rough roads and they say, well, this is the highest load. Or they just take the weight of the automotive and divide it by 4 or something. That will make a big difference when it comes down to determining the safety factor you need. Did you have a question?
You answered it.
Okay. So we have a big range of numbers. The failure of the canal levee in New Orleans was very unfortunate, and when they went back to the design, say, oh, safety factor of 1.3. Well, it turns out that that's what they designed it for, and it wasn't enough. And when Professor Eager talked about learning from disaster, that's an example, because even though you were supposed to have that 30% margin, and it's big, it's huge, it's relatively easy to analyze and inspect, I think there were issues with the soil. There were a lot of things going on that were hard to predict, 50 or 100 years before. And that's why at the end they didn't have the capacity they thought they had. So it was clear that in this one that the water level was not higher than what they designed it for. So in our analysis, when we look at two things, we look at the capacity of the structure and the load applied to it. So the load was taken into account in the design. It's not as if there was an earthquake happening at the same time. It was just water level. The capacity was not quite what they thought it would be through the design life. The aircraft structures, I put a 1.5 safety factor because 1.6 maybe would be the one that I've seen most. I worked for a bit at Bombardier Aerospace. They make small airframes. And at the end of the day, you go to a lower safety factor around the landing gear. It's typically very well inspected, very well determined. They have sensors everywhere to know exactly what the load history is for the landing gear. And therefore, they can afford a lower safety factor. You save weight, tremendous amount of weight. And also in being a very controlled condition, you reduce the risk for something completely unusual to happen. If you have regular inspections, you're more likely to pick up on small cracks that will grow than if you say, I'm going to build it strong enough and it's not going to be accessible for inspection, and therefore we hope everything is okay for 20 years. And that happens, in some small aircraft structures. You can't really see inside the wings, and therefore they don't really get inspected. And then all of a sudden, you have cracks 6 inches, 8 inches long that were not protected by design because there's all sorts of twisting modes that are harder to evaluate. So when you go for your safety factor in these structures, inspection will come into play, and how much you know precisely what the load is. If you have a tension member and the aircraft weighs only so much, and you have to know the landing load very precisely anyway for the overall analysis of the aircraft. and you're right at that starting point. So it's relatively easy to make a very accurate analysis, and you use a material that's also very predictable. Some steels used there, like a 4340, is not going to stress crack. It's not going to do anything crazy that you wouldn't expect. And it's typically designed for a short life. It's not allowed to corrode. So you can put on most of its capacity to use. And that's very unusual. You would think, well, the landing gear should have, very high safety factor, because if it fails, it's a big deal. But the probability of failure is low because you don't have that much variation. And that's one of the things we'll talk about variation in one of the next slides. For buildings, we have this factor of 2, and maybe Professor Eager already said that. Factor of 2, you can think of it as the difference between static and dynamic. It's not really what happens when you can't consume your overall safety factor just by saying the load may be twice as high, because there are a lot of other things that may be happening that you haven't taken into account in the design. But it gives a starting point. If you put together a trailer or a general structure, safety factor of 2, you try to evaluate the load, pretty good way you can. You evaluate your joints fairly precisely. If you have a safety factor of 2, it's kind of a starting point for if you don't have a lot of experience, in that specific application. For pressure vessels, I already mentioned that they have their different ways of evaluating stress level, and that's why in their code they have a very high safety factor. But again, it doesn't mean you can pressurize it 4 times what the nominal pressure is, because then when you get to a transient situation, a water hammer or anything can happen. Thermal expansion will also consume some of the capacity. You can have a failure. There's also aspects that I haven't mentioned up to this point, but fatigue is another parameter. When you decide your safety factor, you have to think about whether you're considering fatigue or not. If you are going to do a fatigue analysis for what your strength of the material is, the capacity, then you can reduce your safety factor because you just know more. You're less ignorant. I got 2 examples here. This is somebody, I did a big project for them, and then he had a fancy high-speed boat he was using in Florida. It's about a 4-inch diameter axle, connecting all the way, sticking off the hull in the back and connecting the prop. It went only to, I think it was a season and a half. So he was into his 2nd season, and the prop fell off as he was on a ride. So he was really surprised. That's why he brought the piece. He wanted to figure out what happened. Because it was fairly high performance, and it's not really a catastrophic failure. I mean, it depends how you look at it, but the boat stops, and then you need to use the radio and get somebody to pick you up. It's not that bad as opposed to other types of failure. So they had a very low safety margin, and this was a type of prop that sticks out the water half of it. So you only have the lower half in the water. If I try to do here, let's see, I'm out of luck. Huh? Where are the chucks? I have to bring my own stuff, maybe. That sucks. All right, no bad writing today. So it's fits sticking out half of the water. You have a lot of bending in that axle. And as the shaft rotates, what I would expect is to see cracking initiates all around, because that highest load would change location as I rotate. Unless I have an unbalance in my prop or something like that, maybe it could be localized. So the first observation here, they had some scars on the external surface of that shaft, right where the seal was, and essentially the shaft was moving enough to hit the metallic ring connecting between the inside and the outside of the hull. And I was only seeing that at that one location where they had cracking. So right from the beginning, it was clear a little bit, and that was not taking into account, essentially it started out as a clean shaft that had, you know, the mill finish and everything, and then when you start making scars into it, especially if they're running transverse, you'll end up with reducing the resistance to crack initiation. And by looking at it here in the microscope, what I found is a lot of cracks. And that's just a general phenomenon. When you see a lot of cracks starting, it means that they started all at the same time. If you only see one crack, it means that it started and then it took over the whole area. So the only way to have 6 different cracks to begin with is they pop out essentially right from the beginning, and they compete with each other, and then eventually they merge. So it means rapid initiation. So rapid initiation, we already know we're spending most of the life of that shaft growing a crack from the initiation area all the way to here, the overload line. So in terms of safety factor, it's relatively predictable. If you happen to know the crack propagation resistance, the fatigue crack propagation resistance of that shaft, you can tell relatively accurately how many cycles it's going to take. Say you start the crack first cycle, how many times it's going to take to finish with an overload failure. And what I've learned after the fact, after examining it and saying, well, this was going to fail no matter what. It was a relatively low safety factor. That was my conclusion looking at it, that the load was very significant, that there was already scars to initiate cracks, and there wasn't much to do to prevent it. Maybe avoid the scars here by having a little bit bigger ring, metallic ring, to hold the shaft at the exit from the hull. But so what I found out a couple of weeks later is the designer of this system only expected, thank you so much, expected about 400 hours of service life for these props. I guess the owner was just not fully aware of it, and that was just about what they had done. So altogether, it did survive the expected service, if you will, which was very limited. But again, we're not dealing with a critical application, and maybe they were considering that worst case scenario, that there was going to be a scar somewhere on the shaft to get the crack started right from the beginning. So this was essentially failure at the expected life, but the owner didn't remember it or something. So low safety factor, a relatively conservative way of evaluating the crack propagation, and it worked. Will it work all the time? No. You can have bigger scars, or you could happen to have higher load than expected from all this movement of the prop, and the safety factor of 1.2 in my mind is fairly low, given what I saw. I would just make it a little stronger. I would probably try to control the surface condition, try to avoid this cracking, because all the other areas that didn't have these big scar didn't initiate crack, even though it was rotating. So it is an indication there was really a weak point around the circumference. So that would essentially increase my practical safety factor if I avoid these big scars and my service life is going to be definitely higher. Any question on that one? We'll may tie back to it when it comes more appropriate.
Why would you have ever designed a boat shop that was only going to go for 400 hours or whatever?
Yeah, well, it was kind of a competition type of boat, so it has to be light. It's extremely powerful. It would just jump right off the water, and still a big boat. So everything is to the limit. And you do that also with some yacht. If you have a competition sailboat, they'll have these little titanium anchors everywhere, and it's at the limit. You can't have corrosion. You need to put the CP on it when you shore it. It's really designed for competition. Minimal. So
it's something he should have known. He should have replaced.
Yeah, you have to be essentially an expert user on these types of structures. If you're just a consumer, you won't be able to maintain it properly and make sure you don't have a hurley failure, or you control those failures. That's right. That's a very good point. So if I want to have this very fancy boat, I'll probably go regularly to my mechanic and say, you are in charge of making sure everything gets replaced whenever it needs to be replaced, because there's essentially a maintenance schedule that needs to be put out. That's a very good point. We'll talk a little bit about the bridge collapse in Minneapolis. That happened, I believe, in 2007. It wasn't at rush hour traffic, but kind of just before it, I believe. It was late in the afternoon. It was a very hot day. So if you're thinking about a steel structure, a very hot day means thermal expansion. It has probably had something to do with it. There was a lot of dispute because this collapse was investigated first by NTSB, and then MnDOT took over, and then experts for the different parties involved also got involved into analyzing how it all happened. So you have the bridge to begin with. It only had two main trusses, one on each side. And it's connected here in such a way you fail one of these connections and the bridge is gone. Everybody's analysis proved that. Now, despite that fact, they had URS, is a very large construction company, look at the fatigue life of they did some assessment, fatigue assessment of the structure after approximately 40 years of service, and they only looked at the members. So you read their report at the end, they say, well, the members are fine, we don't know for the joints. So what good does that give us is really nothing. You shouldn't do something to feel more safe, while in fact, you're not looking at the right thing. So I would say around 80%, I believe, maybe between 70 and 90% of the failures happen at joints, especially if you're looking at a structure that's that complex. In this case, we were looking at gusset plates. So you have members connecting. So say I have a member here, a diagonal, and then I have another one here connecting to a main truss. So I'll just put what they call a gusset plate over the whole thing, with a bunch of bolts and rivets to connect everything together on both sides. Now, apparently, and that's what the government found, whenever I present these cases, I was involved in it, so I can't talk about all of it, so I'm mostly going to do pieces that can be helpful to you guys, and mostly public information that was provided by some people that did the testing. So what the people at NTSB had done is they went back to the design drawing and they looked at the thickness of that plate here, and somebody said, well, it wasn't thick enough according to the rules of designing back then. Well, that's not good, because if we start with a safety factor of 2, but we miss out on the thickness, right from day one on the erection drawing, we don't have a safety factor of 2 anymore. It's less than that. And then you can imagine that after 40 years, that bridge, they added lanes, they added pavement, they had corrosion, and came down. If you add it all up, there wasn't any safety factor left. The load applied exceeded the capacity of those joints. Was there ways to prevent it? Of course there were. These inspections that were going on, regularly, not every year I believe, but maybe every 5 years, they had inspectors. Whether it was a little inspector or a super big inspector, it's a little different when it comes to maintenance than when it's a new structure. We have a lot of infrastructures everywhere, and essentially the government agencies have to put priorities on how many times they're going to do it and to which extent and who is going to do it. When we were talking about learning from mistakes, here's another example where after the collapse they added a whole chapter on the inspector's training class on how to evaluate gusset plates. Because they realized it wasn't something described in enough details, and at the same time it's not that much more complicated. You do need to go back to essentially evaluating the safety factor on the original drawing. So you'll expect a steel structure to be relatively deformable. So if we look at this here, the different members, they had a very good safety factor. But when it came to the connection, it was essentially a question whether, say you need some compressive strength in one of these, say this part of the leg, for example, and it bows, well, now you don't control the angle. It's becoming more like a spaghetti. So if you're going to do an assessment and you realize your thickness here went down 25%, well, in bending 25% is very significant. It's not just a 25%, it becomes more like a factor of 2 in buckling resistance. So these are the kind of things that have to come into evaluating, I'll call it an old existing structure. So things that were not taken into account at the beginning. We had factor of safety of 2. Well, you look at it after the fact, it's not, it's not 2. You just try to figure out if you lost 50% of your safety factor or if you lost all of it. That's what it boils down to. And you hope that it was actually designed with the intended factor of safety, which is not always the case. So a very sad story. I was investigated for a while. And one of the issue was also the rollers here to allow for expansion and contraction of the bridge. It's clear that they were not moving as much as they were supposed to move, which means that the bridge was warping up and down or sideways or in some form of ways over time, and that was not taken into account in the original design as well. If you do it symmetrically, say on the east and west here, that may or may not be a problem. But if it turns out that one side is stuck and the other moves, then you start wrecking your bridge as you go back and forth from one season to the other, and it becomes a problem or a potential problem. So on a big structure like this, I would say when you're designing it, I think it's very hard to take all of it into account, and that's why you put it here as a safety factor of 2. But like I mentioned in the introduction, it doesn't mean you put half the boats, because a lot of it are things that are very hard. When you're designing this, you don't have the ability in general to create a full 3D nonlinear plastic model that will tell you exactly what's going on in each member, each connection, each gusset plate. It's based on codes and standard methods of designing. And when you go off of it over time, for various reasons, then your actual factor of safety is going down, and you hope you accounted for enough of it. Yes?
How many people were hurt?
So the question was how many people were hurt. There were quite a few people on the bridge, so it's more than hundreds. It's in the 100 range, and it's less than 100 that were severely injured or died. Pressure vessels. I want to talk to you about two examples. The first one is just a simple pressurized stainless steel tank in a food processing plant that was mostly intended to, hold, I think, tomato paste or something like that. So it's not especially, corrosive, but it has to be clean. So it was a nice stainless steel tank. And it turns out that it was a heated process. So they had a jacket around the tank. Turns out the jacket had a lot of chlorides in the insulation. And therefore, something that they were not expecting did happen, which is called stress corrosion cracking. It started to crack from the outside of the tank. So say we have it here. It's pressurized. So it started as a little crack running this way. And then at the same time, I also saw cracks almost going in random direction. It will look a little bit like this. Now, when I see that, and I know my stress level in this direction, so for a load applied, so the hoop stress this way is twice what the longitudinal stress is on a closed pressure vessel, I know there's a problem, because it means that my cracking doesn't vary much with my stress level. It's just cracking. So even though I started with that factor of safety of 4, which would typically be with respect to yield stress, I can have stress corrosion cracking at a load 1/5 of that yield stress, depending on the chloride environment, the temperature, and all that. So all of a sudden, I don't have a safety factor. Now, in that particular case, it's really a problem with respect to what I expected the capacity to be. If you expect a ductile behavior of a piece of steel and it fails in a brittle manner, that will make a huge difference with respect to safety. And that's pretty much what happened there with that stainless steel tank. I mean, in normal condition, it would just crack and leak or do something like that. But what really happened instead is it's just started to crack, and these cracks all connected, and eventually it's a big piece that came off, and it was over pressurized as well. So there were a bunch of issues going on, but one of the main contributors here was unexpected failure mode. And that's the idea I wanted to carry here. And it's one of the reasons we have a high safety factor. I've done another project that was for a steam piping system connecting in Washington, D.C. with, we didn't go to the White House, but it was supplying the whole government building area. And we looked at a drip leg that essentially was collecting the condensate. So say you have a line, and at the bottom of the line you have a jump here between different sections. So in the manhole you have a little drip leg here that collect the condensate and redistribute it back to the system. So the connection here at that drip leg was built in an unusual way. So it had the proper material thickness, but I'll show you the detail of that one so you get an idea for what may have happened. So the pipe was running, so I'm going to show the pipe running this way. So if we start from here and we have a leg that's connecting straight through, so it looks somewhere like this. So it's really two tubes connected one another. This one is smaller. That's our leg. Oh, and we're actually going to look at that cap right here. Yeah, let's do it this way. So that's how it looked from the outside. So instead of having a bottom that would look half a sphere, something like this, and therefore you can put a weld here, and the weld is essentially subjected to the same load as the wall next to it. What they had the weld in this corner, and when you pressurize this design detail, it just wants to expand. So you're cracking open those welds. So you started with a safety factor of 4, 5, 8, whatever it is. Now, instead of having just a tension stress on the welds, if I blow this up, the way it looked like is they had an end cap like this. They had the wall here. And it was sort of welded here. So what happens when you pressurize this cap wants to bend out and become more like half a sphere, and create tension here at the toe of the well, at the root of the well, I'm sorry. So the toe is right here, but at the very root of the well where you can't really control the quality, you know you have imperfections there, that's where the highest tension was. So unzipping from that toe was not a very hard process. It's not something, well actually this part of it, the code says you're supposed to use these kind of caps or find a way essentially not to put the highest stress on your welds, because otherwise there's no point in having these thick walls if the capacity of your connection is only half of the capacity of everything else for this application. So we were looking at something that was 3/8 of an inch or maybe half an inch thick wall, a little more than maybe 3/4 inch cap, and it had this well that was, you know, pretty much the same size, but loaded in tension at the root of the well, so no more safety factor left. When the transient loads came up with big water hammer, this was really ready to go. So that's how you consume safety factor.
So was that how it was designed, or was that a decision made during construction?
I would say nobody was able to show the exactly who made the decision. So it was possibly part of a repair, and that's part of the problem sometimes. So if you go to a repair, they'll go and they know they have to use the right thickness, but when it comes to the detail and how to do it, that's probably where they were lacking proper engineering of it. So if we looking at these factors of safety, and we're trying to decide, do we need 3, do we need 2, 1.2, 4, 5, 8? I've seen designs that have safety factor of 8 actually, and people can still break the stuff, but not the way it's supposed to be used. Even the little propane tanks, for if you want to solder something, you go to Home Depot, you buy the little propane tank with a torch on it. They have high safety factors, but if you drop it from 6-story high, eventually something bad can happen. Well, okay, we talked a little bit about material strength, and I said something like, if I have my steel 4340 on the landing gear and it's going to be inspected, I know what I'm getting, and it's pretty much true. If I deal with a casting, for example, I don't know as much, and a lot of times with a casting we have an additional factor of safety that we put in, because or we're going to inspect it a lot, there's going to be something additional, it's not as predictable. If we're looking at the environment, it's a good example when I showed you the chlorides from the jacket of that pressure vessel on stainless steel. Is if I don't take the risk of slow cracking into account, or if I cannot rule it out, then I need a higher safety factor. Actually, I should figure out whether there's a risk for that environment to be there, temperature, moisture, and chlorides. in the case of stainless steel. But the less you know, that's my factor of ignorance here. The less you know, the more of a safety factor you need. And sometimes it's not a question of effort. Sometimes for an application, you just don't know all the possible environments. So you have to be more conservative than if you have your landing gear and it's going to be inspected regularly. You don't allow for any significant corrosion to take place, a very controlled environment. Then you reduce your safety factor. Now, essentially we have two aspects to the factor of safety. One is the we don't know part. And then there's the one which, what exactly, ultimately, do we need? What are we willing to go with as far as failure rate? And that's independent. And was typically built from experience. Those bridges, we'll go through the numbers and how it's calculated later, but you're looking at a 10 to the minus 6 chance of failure. 5/10 to the minus 6, something of that order per year. That's the probability of a bridge collapsing, approximately. And I'm sure it varies, but it's the kind of average intent based on all we know about factor of safety and everything, and things that we don't know that make that factor of safety goes down. And also take into account all the inspection. It's kind of after the fact analysis. And that's why, and that number, 5 to the 10 minus 6, will be different if we're looking at a car. We could have a lower number. I mean, most of the time people crush cars even if the car is perfectly fine because they're not looking where they're going, or they're talking on the phone, or whatever happens. So you don't need the same overall low failure rate if you're talking about a car than if you're talking about the bridge. I guess that's the idea I want to carry around. For one, you got a lot of people on the bridge. And the bridge is going to be there for much longer than the car, too. So how do we do this design? And this is a topic that we elaborate a lot in the fall class. So I'm just going to give you guys an overview. There are different design methods. I've talked about fatigue crack propagation, the landing gear, and those things. So this is kind of one way, damage tolerant analysis. And you can have other simpler design where you just go and say, well, I think this is going to be the static load. I'm going to put a safety factor of 3 on it, and hopefully everything's going to be fine. If I don't have a whole lot of fatigue going on, if I don't have stress cracking or any kind of environmental damage, that'll probably be fine. And the other point is it varies from one industry to the other. So the approach varies and the safety factor values varies as well. And what people are willing to go with in terms of reliability. One sad example of that is these blowout preventers for sealing around drill string for drilling. So you're looking at the disaster with the BP spill or the Macondo well, Deepwater Horizon, no matter how you want to call it. These valves are clearly not designed with a high safety factor. Is that acceptable? Well, it's just the way it is for now anyway, and it still is. And one of the reasons is if you have a blowout in normal conditions, you may have a crew of 15, 20 people working there, and they know it's coming. So a lot of times they do have the opportunity to escape. And therefore, I've seen projects. I had 4 or 5 well blowout investigation. A lot of times nobody gets hurt. It's a lot of money lost, or it's a lot of environmental damage in the case of the BP spill. But there used to be that sense that it's just money. It's not the end of the world. So what happens with the BP spill is different. It was really deep, and It just didn't shut itself up. A lot of times, the pressure burst will just blow all the drilling mud and some of the gas to a point where you reduce the pressure in the well itself, and the well collapses. The casing just breaks and it seals itself. You can't, you lose your well, you have to drill somewhere else because now you lost all the integrity. But it's not, every time that it will just blow the gas and the oil out like it did on Macondo. So that's kind of one example that I come up with as an industry where the American Petroleum Institute is not really prescriptive on what a safety factor should be and how to test it. And the practical consequence that I've seen is, relatively low reliability of those valves. Now, how do you make it reliable? We talked about safety factor, but I want to stress out there's a lot more to it. If you go back even 30 years, so when that bridge, the Minneapolis bridge, was put together, they couldn't do even finite element that we would probably do today for such a bridge, given the details that were in it, or we wouldn't do the details. But so if you start with a bridge and you have your safety factor, down the road, it's by experience. So if we've been building thousands and thousands of bridges over a 100-year period this way, and we get the failure rate that we're willing to go with, there's no reason to change the overall safety factor. If we're getting more failures, a little bit like I would say is happening with the valve for blowout preventers, then you have to raise your safety factor. You're just not good enough. And that's the experience aspect. If you're coming up with new products, you may do a lot of testing, actual laboratory testing or field testing to see if you've taken everything into account. You do that a lot in aerospace. I remember, for example, the wings for small jets being moved up and down, so they held where the fuselage is with all the bolts on, and they just moved the tip of the wing at least a foot up and down to go through excursions, maybe more, a lot more than that. And they had the extreme one, so the very last cycle was kind of all the way until it breaks, and it was a lot of deflection. And when you get into high deflection, now you start thinking about what happens to the seals and the setting for the gas tanks that are in the wings. So it becomes also an assembly level evaluation of your safety and reliability. And that happens a lot in automotive, and I work on ATVs and relatively smaller structures where when you put everything together and you have the exhaust, so you have the heat, and you're going to have water coming in when you're running the units. These are not things that are easily taken into account with the computer. You need to run your prototypes and find out if you have a problem. It's a very good way to increase your reliability. It doesn't really apply to the primary structure. You don't want the frame to wreck completely. So a lot of times, to know your safety factor for the frame, you do need to do some analysis. But if you're really looking into evaluating if your overall assembly is going to fit the function, there's nothing like a full-scale test or a field test to demonstrate that, and it's required, for a lot of aerospace assemblies, and they do it also in automotive and with recreational products. So calculation's always good, but I guess my point here is if you're only going to do calculations, I would say boost your safety factor because there's so many things, and you may miss out on the integration of your assembly, things that are much harder to predict ahead of time. So when we arrive to those safety factors, I think I mentioned that it's from experience. So I'm not going to tell you that people did a lot of statistics when they came up with safety factor 2. They didn't. There are today a lot of people, and I got a book here, it's full of statistics on how you could relate actual failure rate to individual parameters and stuff. So we'll use some of the ideas here just to get our idea about what happens between a safety factor of 2 and a failure, whatever happened. Because again, my basic line for you to take out today is we don't build stuff much stronger than it needs to be. So we can't think of the safety factor as something that anybody can use for their purpose. So if we go to the lab today and we have 5 welds and we test them, we find out the strength, for example, and tension. Well, probably these 5 welds were made by one guy. If I have other welders do it, they'll do it differently. If over time they are instructed by different people, it will also change. So when you come down to a large population, and I've just put on this basic statistics here, it's Gaussian normal distribution, and we're out here about 1 standard deviation. So it will essentially say 65% of the population here is in the good area, and then you start having failure for the lower 35%. So that's something that can happen if I run these 5 tests. I still have that tail of strength levels that are quite possible coming from different welders, different inspectors, different instructions on how to do it. But I'm not going to know that. So that's why I say after the fact you realize, well, I really need that safety factor because I have variation. That's the idea. If the variation is tight, if that curve here is really tight because we're dealing with a machine steel component, no welds, no nothing, like in the landing gear, then I'll go with a lower safety factor. My standard deviation is much smaller. So that's the book here, just in case you're interested going into the details. It's a lot of statistics, like I mentioned. So what we have here is a plot of capacity, that's the vertical axis, against the stress level. And so it's centered, say, where we would do the design. Say we have here a safety factor, looks like just about 2. And then we know we'll deviate from that. This one is circular, but it doesn't have to be a circle. It's likely, well, I'll take this back. It depends on the application. If I'm dealing with a pressure vessel, and I know I don't have transient regimes, I would say I know my stress very well. So in the horizontal axis, I could make this circle more an ellipse pointing up and down because I know my stress level. So my uncertainty about that one is going down. For that same pressure vessel, if I don't know all the chemicals that may be used in it, or the kind of jacket it's going to have, so my material variability may grow, so that would make a vertical ellipse. If I'm looking at something else, say I'm designing suspension for a car, and I'm making it out of steel, I know pretty much what the steel will do to me if it's not welded, if it's forged. So I'll have a relatively narrow variability in capacity, but then what people will do with the car, don't know. It could be very terrible. If you take scenarios, they burst the tire and then the wheel hits the ground, and whatever happens, you can get to higher loads than what you would even make a measurement of in a field test condition. Yeah, I would say hitting straight with the wheel decreases your damping factor, and that's where you essentially generate more stresses in the suspension. So if you want to make a very detailed design and take into account what I just said, then you can put this target closer to the failure boundary because you're reducing your variability, or you're taking a worst case scenario. But if you're making an analysis based on the weight of the vehicle and thinking, well, maybe it's going to go on 2 wheels or something like that, then you need a higher safety factor because you're not taking everything into account. So it's the general idea that it is not a factor of safety of 2 because I have variability in capacity and I have variability in stress level. Now, what do we need at the end of the day? And that's when we talked about to a 10 minus 6 type failure rate for bridges. What we're looking here is at this portion, now it's a 3D representation of the same thing we were looking at, where we have stress level and capacity. Where is the cut defines how much failure rate, how many failures you're going to get per year or per 100 years. It's a very important number. At the same time, we cannot do the math to know exactly how to design different things starting from that principle. It just helps us realize we have that factor of safety, but it's, I don't know exactly what, I don't want to come up with a new term for it, but I think you realize that it is there for safety. That's true, but it's not really the extra margin that you have. You don't have too much of a margin, and we'll go there. It's just about time. This is how people define failure rates. So I was talking about bridges that have a lot of people on them. What happens here is you have T and L. The T is the number of years of service, and L is the number of people that could be affected by a failure. So if we're talking about a bridge here, we're boosting up that L by a factor of 1,000 with respect to a car or other things. And that's why in the end of the day, it's just the idea. I mean, you look at these numbers, they're not very precise. But it's the idea that depending on what you're doing, if you have an offshore structure, which we talked about, what a big deal. There are only going to be so many people and they're trained to escape, except for the environmental spill aspect. So that's kind of the idea on how ultimately we want the failure rate to be. But you can probably see there's really no correlation whatsoever between that failure rate, that's what we want, and the factor of safety. I mean, I haven't tried to plot it, but it's so different because the factor of safety is tied into the variability that we talked about, which varies from one industry to the other. And it also is function of our design approach. How exactly are we calculating stress? How are we evaluating capacity? And it's the combination of the factor of safety. I'll put the method here. What else did we talk about? We talked about variability. And I'm sure there's more, but if you start at least thinking of these three factors giving you a probability of failure, we're on a much better track than if we're just thinking, oh, we're just going to raise the safety factor. You can just use a more precise way of calculating your worst case scenario, but get more knowledgeable about all the possible failure modes and like stress corrosion cracking and eliminate them. Now that safety factor of 2 that we started with, say we start here, safety factor of 2, that will give us within 1 sigma interval, so plus or minus 15% of the time, so maybe 30% of the time, it's going to fail. That's not good. So it's the general representation when we're looking here at probability and we have this stochastic safety factor. That's the actual ratio of capacity over demand. After everything that was not taken, it's not by design, it's actual. So you can see that if we start with a safety factor of 2, and what we want is a 10 minus 6 probability of failure, as a general case here, this is not always the same. It will depend on our method and variability. But as you want to reduce your risk of failure, your actual factor of safety goes down. So the probability to have one failure in a 10 to the 6, if I start with a factor of safety of 2, means that I only have a 20% margin. And that's I think the best demonstration where when I said put all the boats in, that's why. Because you don't have that safety factor of 2. If you put half the boats, probably you have a 30% chance of failure or something like that. So that's the range that we're looking at as to what is our nominal factor of safety as opposed to actual or stochastic here. This made me think, you can relate to this, and when you start with a factor of safety of 1.2, then you get to a failure rate of 10%. It's a little sarcastic. It means 10% of the time you'll actually fail if you start with a 1.2. But again, the variability and the method will influence the shape of those curves. So you can have a long service life with a factor of safety of 1.2 if you very conservative and detailed in your method and you take into account all possible variability in terms of both the material capacity and the stress level. That makes sense or no? Yes? Good. Go through some examples. And now, so what I tried to do, I hope you realize, is bring a little bit theory along with some examples, and I'm happy to discuss and get some feedback from you. This is kind of a new put together, but the idea is mostly to be as conscious as we possibly can on what that factor of safety means, or safety factor. The spar for a helicopter blade. What we're looking at is a cross section of that blade, and it has an aluminum spar at the front here, and then a honeycomb core structure with an aluminum skin all the way to the back. So this could be about a foot across from the tip to the tail. It's subjected to a lot of load just by rotation. So if I draw that blade from the rotor, you rotate at high speed, so you'll have the centrifugal force creating tension this way. So we have the leading edge right here. That's where the highest tension is going to be because of what I call the drag force. So we have the wing, the air pushing the blade backward, creating that bending moment in the rotation direction. And then we also have an uplift. Otherwise, the helicopter wouldn't be that helpful. So we can tell right from the beginning that we're looking at the highest tension right under that nose here, because that's where you have a combination. You have tension generated by the centrifugal, by the uplift, and the backward load. Now, do we know that load precisely? No. The best way to get it that I've seen is they put strain gauges right there, actually close to the rotor, so just before they had the stiffeners. So they put a strain gauge there, find out what the stress level is for different service, going up, going down, taking off, turning sharply. So you get some idea and you can rate it. Say like landing and takeoff will be definitely the highest cycle for this centrifugal force. you just have to decide how many cycles you're going to be willing to go through, and determine the life based on that. So if I say, I'm going to throw a number, so I'm saying 30,000 cycles is what I want to go through. And then I know my stress level, so that would be my number of cycle. Say my stress level max, I'll put 12 KSI. It's aluminum, not going to be too hard on it. So what does it mean? It means that I need a sigma, I'll put it strength because it's fatigue. And minimum, say we add 50% to that, so we'll be at 18 KSI. Well, that's not that easy. It's not that easy to get an aluminum alloy that will take 30,000 cycles at 18 KSI, if you, depending on the surface finish you assume and all of that. But it's the general idea. So that would be designing with a safety factor of 1.5 based on stress level. You don't want to take that number and divide by 1.5 and just calculate for another number of cycle to failure, because these fatigue curves are very sensitive to stress level. So at 12 KSI, most likely you have infinite life, no issues whatsoever. But at 18, now you have a limited fatigue life, and you have to see if you can make it to the 30,000 cycles. That's the general idea. I've done that couple times, I guess, and you can get into like the very fancy. I think you guys all familiar with stress strain curve, SN curves. Good. So you have your number of cycles to failure, you have your stress level, and you expect a curve something like this. So say now we have a generic material, but say normally I'd be able to get 12 for one specific type of loading, if we're looking tension or tension compression, whatever it is, and we'll do the overall range here for stress level. So what I do with because I want a safety factor, I'm looking up, I'm looking at 18, and now I'm looking to see here, given the variation in failure life, if I'm going to get my 30,000 cycles. That's the overall exercise. And we can go through the math. It's not that complicated. Typically, the more data you have to generate that curve, the tighter you can make your confidence interval here, and therefore you can satisfy yourself and everybody else that you do have your 1.5 safety factor. That's exactly how I would approach this in a schematic way. So that's in reality, if we look at it. We have experimental data point. This is very different. Now the stress level are higher. We're looking at some turbine blades data. So it's a super alloy type material. So it's got a much higher stress level than what we looked at here for the aluminum. So this was a situation where they were trying to evaluate if they could change the alloy from one to the other. And given all what we talked about, to get to a good reliability, you need your field experience, you need your testing, large-scale testing, you need calculation, you need all of that. So when you go and change material, a lot of time to make sure you don't affect your factor of safety, you try to compare them with respect to every single property, or at least every property that matters for your design. And that's what we were doing here. And The original alloy, I can't say for sure which one it was. I think it was the blue one. Yeah. So anyway, one alloy is the original, one alloy is the substitution. And given the limited data that you see there, because that happens when we're talking about fatigue, takes weeks for each data point sometime. So it's not easy to get 100 data point and be as sure that you don't have a problem than if you're doing tensile tests. You can do a lot of tensile tests and very quickly and figure out the strength. You're still looking at a cost of material, cost of machining, and everything. But fatigue is a lot more expensive than the other things. So the point here is you have those curves, and you see that they overlap. So at the very end, you have the red line being slightly different capacity. So it becomes a little higher, and you see that on the confidence interval. So those dotted lines are built essentially using the range of data and arriving to what is kind of the equivalent of standard deviation, but for a 2D plot. And you can do it two ways. You can do it based on variation in life or variation in stress level. If you try to do it in Excel, it's going to try to do it with respect, it's going to minimize the vertical variability, but in reality, it's the horizontal variability a lot of times that we care about. So we have to reverse the plot to do the analysis. It's not a big deal, but if you think of it a little bit like I drew here, we're interested for a given stress level how much variability in life we're getting, as opposed to for a given life how much variability in stress we're looking at. That's not really what we're interested in. So it's just a matter of how to run the analysis, which makes a difference for these curves. So we're looking here at probably a 95% confidence. So if we start with a life at 10 to the 7 cycles of 25, our confidence interval, because we don't have a whole lot of data, is all the way down to 17 and 18. So when we're talking about that safety factor, we want a safety factor on top of taking that variability into account. Otherwise, we just consumed all of it already. So it's not, that was not the idea. It's always easy to say, well, you know, yeah, I'll use the margin, and or I only use 30% of the margin. But if your actual margin from that plot here is only 20%, nobody's allowed to it. That's really the idea that I want to stress out. This is going to be really brief here for boats. The main thing I want to point out is, well, you have different grades. So a lot of times we specify grade 8 if we going to have a connection that we don't want to slip. So we preload the boats and it's all tight. It's relatively common in advanced structures. So we're looking at a strength of the material to be about 150 KSI for steel. And then this is a different version of a stress strain analysis for fatigue. So we have the stress amplitude and the mean stress. There was a way I explained that last time that worked. So what do I know about a material? If I don't have a mean stress, if I do a tension compression fatigue, they have data for these bolts that indicate a failure at only 20 KSI. That's low. We start at 150. That doesn't make everybody happy to realize all of a sudden you're reducing your strength by a factor of 7, roughly. The other side of this, so that's the amplitude portion. And then we have the mean portion. For a mean portion, we know that we'll break the bolt at no amplitude, so just an overload, if we go to the 150 KSI. So this simple Goodman type analysis just says, well, between those two conditions, so a tensile test and our nominal fatigue test, we'll just draw a straight line. That's what the analysis is. And then you have to cut it back here because you don't want to exceed the yield. Say you have yield at 120, you see. This is the end of it. So this is our failure line, if you will. Doesn't have much of a safety margin, but there's always the good news. When we preload these boats, if you go from a nominal stress that goes from 0 to 120, for example, for an application, oh, no, that would be too much, it's the yield. Say we'd go to 100 KSI in the application, and that's a good example for a crane, anything that has a big bearing in it, you know pretty much what the load's going to be. So say 0 to 100, it doesn't mean that the bolt experiences that. A lot of times we're actually going to preload the bolt to say around 80 KSI. That's going to be our mean stress level. So we're up here at 80, but it's preloaded, which means that it all acts as a big rigid block as opposed to just the bolt hanging the load. So when you're looking at the excursion for amplitude, it's typically reduced by, I would say, a factor of 6 or 7. I don't remember the exact number. So you can manage to be kind of in that window here where you're in the safe zone because everything is preloaded. So I have the bolt, and say I got 2 flanges connecting to. What happens is everything is really tight. So I tighten this up, I preload, so I got 80 KSI here, and then I got some compression around here too. And all of this is like a rigid block for practical purposes. It's all going to deform in tension compression together, as opposed as if I have a hanging bolt and I put the load on it. Think of it in strain, in terms of strain. So here, say I get a strain of 0.1 percent, probably less, but over here it's much bigger, so the overall variation in stress here is going to be divided by 7, essentially, approximately, because there's no separation. If you exceed, now you're in trouble. Now, one of the reasons for you guys in the context of this specific lecture is to say, if I don't calculate all of this, if I don't go through this method, how am I going to know which safety factor to use? It would have to be 10 or something like that. So the only way I reduce from 10 to maybe 2, or sometimes they'll even use less than 2, is because I know and I understand the detail that even though I started with 150 KSI, it's actually 20, but when I put it back, you know, it goes back higher. I mean, there's a lot that comes into the analysis of the assembly to tell me what's acceptable and what's not acceptable. And some codes may say, well, if it's 150 KSI bolt, use a factor of safety of 5, which means 30 KSI. But now the question is, so is that for an infinite life? You know, it really depends on your preload. And that's one of the problems with those connections. Is you do assume that you're getting this clamping force to generate this, and therefore, you know, it's kind of the things that for a certain application needs to be inspected. For even erecting a regular building structure for a nuclear facility, they have these sensors that collapses when you reach a certain load. DTI, so direct tension indicator, and so the inspector can just go around and see that all the sensors are put in and they collapse to know that the bolts were put on, you know, to a sufficient force. we don't have time to go through the welds. So if you're going to design something, and this is in the context of factor of safety, it's just to say it's just part of this overall process. Say I'm making a recreational unit like a snowmobile. I start with a certain frame size, and I start analyzing it. I do some field testing, and eventually I get something out that may be based on a safety factor, well, let's say 3 for our discussion. So if I start with 3, is that going to be enough? Well, it depends on this. It depends on what's the variability on that safety factor of 3. So did I look at all the welds and figure out that they also have a safety factor of 3? If not, maybe I want to have a little higher factor of safety. It really depends on the specific of the application, and it comes into different parts of the design process. You do want to think about the joints very early on, because stupid example of that is I built a trailer that has all the upper sheet metal and the cover is aluminum, and my frame is galvanized steel. I can't really connect them easily together. I got to put fasteners everywhere. If I do it again today, I'll probably do all aluminum. It may be a little more expensive in terms of material, but I won't have that joining issue. But I think when I started, I wasn't sure I was going to put a cover. So it's kind of part of the process. But when you're coming up with something new, a lot of the things that looks like, oh yeah, we'll figure it out. First, we want to see which material. Well, material combinations and kind of ideas of design, trying to avoid welds in critical location, they may come in very early on. I remember last term we had a student wanted to build this vessel. First of all, he was going to do straight cap, so I said no. So it had to be these domes. And then I said, well, looks to me you're going to need some joints. So if you're going to use a spring steel, thinking that you're going to maximize the strain aspect of the metal, well, when you weld spring steel, you lose your strain. So it's just going to fall back on you very quickly. So that's the kind of things that really in this whole process, safety factor, all ties back, talking about the suspension, these welds here. So you use a certain tube size to resist tension, buckling, but you want your connection to be as strong. So you have to figure out how you're going to make this happen. Is the size determined by the strength of the welds or just the buckling resistance? You have to evaluate those things and decide which safety factor. For buckling, it's geometry. So as long as your tube is straight, you don't have to worry about stress corrosion, cracking, fatigue and all that stuff. So you have a low variation in your capacity for that type of loading as opposed to welds. Welds, you need a higher safety factor because you don't know how good they're going to be. That's how we work this out. We really did the bridge well. Coefficient of variation just says, when we looked at the Gussman distribution for normal distribution, we said if I know I'm using 4340 steel for the landing gear and it's going to be controlled with a certain strength, a certain processing, I just narrow my coefficient of variation, and therefore I get better predictability, and I can use a smaller safety factor essentially to get to the same reliability, and that's desirable a lot of times. I would say it's desirable to reduce your factor of ignorance in general. Because you can, but at the same time you don't want to be fooled thinking that you took everything into account. So there's always going to be a limit that you don't want to go below, and a lot of that varies between industry. it's based on experience, and the statistics, honestly, I think just help explain, why we're doing it, as opposed to being really a practical tool for deciding, which safety factor to use, at least to this point, from what I know. In terms of design method, it's really hard to start from scratch because you have something that works. So you in a given industry, if you're looking at a bolted connection, if you're looking at a well, they'll say this. You hope they'll say this and this as well. You kind of need all three. If you try to do something with a given safety factor without guideline on how to calculate your stress level and capacity and having a very good idea of what the variability is on those, you're out of luck, I think. So that's it. Any question? Yes?
Which, in the Minneapolis bridge collapse, who were you working for?
Okay. It was different types of people, but it was related to the design team that originally put the bridge together.
So you were their retained expert?
Yeah, it was the metallurgists. It was a bigger team. Obviously, they had like structural engineers and all sorts of people. It was fun.
So were there many people that had hands-on experience with the design of that particular bridge, or was it just the organization was still around?
The organization was pretty much dismantled. So it was very hard to get more information than just the original drawings. Okay. Yeah, it's a good question.
But did that bridge, you said it was about 40 years old, was that its life expectancy? Or?
No, you don't expect these to just come down on you.
Well, not to come down, but I know that they're...
Yeah, I think 50 is a rough number, but we have Longfellow right here that's almost 100 years old, and we want to keep it.